Hello, welcome to the review of Quiz 8, Propagation of Error. This is a fun one. So when I was trying to compose the quiz, I reached back into my own past and said, all right, what is the sensor that I've used that we haven't discussed yet that is the most irritating because of this phenomenon, this propagation of error from multiple measurements? It did not take me long for my imagination to wander over to humidity sensors. Humidity sensors are notoriously irritating because they are sensitive to both humidity and temperature. And cheap sensors, they don't compensate for this. Expensive sensors, this is why, by the way, humidity sensors are frequently so expensive. Good sensors compensate for temperature so that you get a measurement, a well-calibrated measurement regardless of the air temperature. But cheap sensors, nope. It's not like that. You have to do it yourself. So I just poked around at the internet, and it did not take me long to find an inexpensive Honeywell sensor that was not temperature compensated. You have to do it yourself. And when I simplify the raw information from the datasheet, if you're curious, you can click on the link. It's there. When I simplify that, the expressions that you get from that data sheet, I wind up with a calibration that looks like this equation here. So we're in this scenario, you're using this sensor in an environment where you don't actually know the temperature. You assume it's going to be 25 Celsius, but in reality it's going to vary around that. This actually is a really good example. We're going to treat it as if it's random error, but this is a really good example of systematic error because probably the temperature isn't going to vary randomly. It will probably be fairly consistently wrong, right? And it will obey patterns. So in the summer it will be consistently hotter, and then in the winter it will be consistently colder, right? So probably this is not really a random error. But for now, let's pretend it is. For now, let's pretend that the sensor's in a bunch of different environments, and there's just no predicting what it's going to be seeing, and it really does. Let's pretend that its environment really does vary randomly, and we can't predict what temperature it's going to see. So that's the scenario you've been given. And these are all these numbers here. I yanked these straight out of the data sheet, right? So these are nominal calibration data. Okay, so in the scenario, the sensor's being used to measure humidity in a room, but you don't have that temperature measurement, like I said. Okay, so we're going to presume delta T is 0, that we're sitting right on top of nominal. So this is easy, right? So it's just saying, hey, plug in these numbers and see what you get, right? So this is the easy one, right? All right, no problem. So I'm just gonna click over to my work. All right, here we are, and we're gonna just copy the. Whoops, I can't quite see the formula. There we go. So relative humidity ends up being AV plus B divided by 1 minus C delta T. So when we just plug in verbatim, we've got 32.26, and that's per volt. I'm going to be sloppy with my units and leave them off. My voltage was 2.9 volts. Whoops, I said I was going to leave my units off. Alright, so that's the volt value for the voltage. The offset B, I think it was negative. Yeah, negative 29.03. Cool. Okay, and that's divided by 1 minus C. I'm going to go ahead and write it out even though we know it's 0. Delta T was 0. Okay, so this is just nothing. Not bad at all. So I click over to my handy dandy Python terminal, and 32.26 times 2.9 volts minus 29.03. And we have 64.5% relative humidity. So ASHRAE, the American Society for Heating and Cooling, Heating, Refrigeration, and Air Conditioning, I think is how it goes. So they recommend for humans humidity is between 40 and 60%. So we're a little bit humid here. So 40, anything below 40, and you feel dry. The membranes in your the mucous membranes in your nose start to dry out, and it feels uncomfortable. Your lips will start to chap. And the drier it gets, the more that's a problem. Anything above 60, it starts to feel clammy, right? But really the biggest problem for this for buildings is at high humidity you run the risk of mold growth, as mold can survive in the building, and that's not good. So typically the reason you want to keep humidity under control is so you typically want to keep it between 40 and 60%. Humidity is the guidelines I've read. Okay, so this is a little humid, but not unreasonable. All right. So question 2. Let's quick back to our. So we've got the sensor reading. That's the nominal sensor reading. Now, find the sensitivity of the measurement voltage. So in other words, take the partial derivative. No problem. Can do. So we need to take the partial derivative of relative humidity to voltage. Well, I'm going to treat this denominator as a coefficient. Fine. And then the derivative of this numerator thing here is just a. Easy. When we plug in values, well, this is still 0, and so the answer is just... Well, that was hard. Yeah, so 32.26. Done there. All right. Question 3. Find the sensitivity of the measurement to temperature. So now we have to take the partial derivative with respect to delta T. This is a little trickier. Still not insane. All right, let me get my work up here where you can see it. All right, so when I differentiate this with respect to temperature, right, this is the same thing as being up top, but with a negative exponent, and so I just carry that negative exponent down front. Right, I'm going to leave the AV plus B. It's just a constant, right? Everything else just looks like a constant when we do partial derivatives. And it's going to be times 1 minus C delta T to the negative 2 power. Now, don't forget, I need to multiply by the inside derivative. That is the derivative of the thing inside of this. And that's just negative C. So these negatives are actually going to cancel each other out. Let's think through that to make sure we've got the signs right. If the partial derivative of relative humidity with respect to, oh, excuse me, I'm sorry, not V. Oops, that should have been delta T, sorry. The partial derivative of relative humidity with respect to temperature is positive, which we're saying it will be, then that means an increase in delta T needs to increase the relative humidity measurement. So is that true? Well, let's go back and look. So if I increase delta T, it's going to, oh dear, decrease the denominator. Oh, so it will decrease the denominator, which will have the effect of increasing the ratio, right? So yes, that is correct. An increase in delta T increases this ratio. So yeah, it looks like there's an idiot check that we pass. Okay, so now we just need to plug in. As it turns out, this is actually pretty simple. Let me just rewrite what I've got here to make it a little easier to interpret. Yeah, same thing. So yeah, I just rewrote it to make it look a little nicer. This is, as it turns out, when we plug in, this is still 0, and this is still our 64.5. Just now it's going to be times C. So that's going to be equal to, what was C? 0.00216 times 64.5. Click. Okay, and there we have it. So that's 0.139. So per degree Celsius change in temperature, we only have 1/10 of a degree error that implies a deviation in the measurement. So this is per degree Celsius, are the units there. Okay, that's it. And so that is the answer to that question. All right, click. All right, so assume the standard deviation, so we've got a standard deviation of voltage, we've got a standard deviation of temperature. Now we got to piece together the total, the standard deviation of the humidity. So clearly we just need to add these two no, no, that's not what you do, right? You gotta sum the variances, right? We know that. We know we sum the variances, right? So the variance on relative humidity is going to be remember that? Plus delta T was my other one. Okay. So I need my 32.26. Man, that decimal is hard to see. Sorry about that. All right, so 32.26 squared times the voltage variance was 0.05 squared. Again, being sloppy with my units, I'll deal with it later. If you want to carry your units through, of course, that's really good practice. It makes for cumbersome scratch work. So I have a tendency to be sloppy. And we said that there was about a 5-degree standard deviation, which is not insane, right? So when I was an engineer with ESOB, we would design all of our equipment assuming 40 degrees Celsius operation, which is 15 degrees over nominal. And yeah, and pretty hot. 40 degrees Celsius is a little uncomfortable. Okay, so let's figure out what that is. All right, we're done, right? Just write down 3.08. No, we are not done. We need to take a square root, right? We need to take a square root. That is the variance. So I have calculated the variance is 3.085. And that's going to be in relative humidity is a percentage, so it's dimensionless. Okay, so let's do a quick idiot check and make sure that all works. This term is going to be on the order of a half squared or a quarter. This term is going to be on the order of 1.6 squared. Yeah, so that's really where it's coming from. So if you were wondering where most of our uncertainty comes from in this measurement, the answer is the noise. It dominates, right? This term ends up being about 1.6 squared. So the variance is about this actually. I think that's the square root of 3 is very nearly 1.6, so that's really dominating. Whereas this is only a half squared, ish, a little bigger than a half. So yeah, if you wanted to improve the measurement, man, this is what you need to do. You need to reduce this. Okay, so to find the standard deviation, then we just take the square root. I'm running out of space. Oh, apparently I didn't do that. Fine. We'll do it that way. There we are. 1.756, we'll call it. That's crazy amount of sig figs. 1.756. All right, and that's the answer. That is our estimate for the resulting standard deviation in relative humidity. All right, thanks for watching. I hope this was helpful.